In this system, we're going to be looking at the oscillations of the tail of a helicopter. We're going to be compensating for the mass of the tail section itself when we are going through these calculations. So, in starting with the modeling step, as we typically do, we want to see how are we abstracting this system and where are we eventually going to be arriving with it. So the tail section is going to be rigidly attached to the fuselage of this helicopter. So because it's rigidly attached and we're only considering the tail section for this, we can treat the tail like a cantilever beam that's going to be rigidly attached at the left at that point A, and then it's going to be a free connection at the other side, and at the very end of that tail section we're going to have this tail rotor assembly that's going to have its own mass in the system. And then because we have this eccentric mass that's going to be rotating around, we're going to have some forcing function acting at the end of this. So we're going to say that this has some length L, which we are told is going to be 4 meters, which we'll take into account. The cantilever will have a rigidity to it. It's a deformable object. So we're told it's flexural stiffness, which is E times I. That's given to us. And we are given the mass here of the rotor. And what we want to know is how much does the end of this oscillate. I'm going to call this, for the purposes of the picture, our V, so we don't confuse it with some other variables we're going to be using, since this will be how we define X going from left to right. Okay, so in our modeling steps, where we want to go is, because we are going to be compensating for the mass of the beam, I'm going to go one step down and say I want an equivalent massless beam where this heavy mass is going to be on the end. I'm still going to be applying this force to it, but I'm also going to have this M effective at that same location. Now I'm tracking this V the whole time. Right, so I've taken the mass out of the beam. It will still have rigidity, which I'll go one more step and model that. But I'm putting the effective mass, I'm accounting for the mass and the weight of the beam itself, the kinetic energy of the beam, and I'm putting that into this MEF, this mass effective. Because ultimately where we're going to go with this is the last level of abstraction. This is going to act like just a spring mass system, where we're going to have some equivalent mass, which we're going to see is M plus M effective, on some equivalent spring constant that we're going to be finding, and it's going to displace vertically some amount V. Right, so we're treating it as a 1 degree of freedom system. We're still going to be saying for the beam, if we know its deflection at one point, we know it at all points. So we're going to be just tracking that V and getting it down to this level where we have a mass and a spring, and we're also going to have that forcing acting on it. So it's going to be acting in this example as an undamped forced system. And once again, with deformable objects, they should be in reality dissipating energy, but typically we are going to be ignoring that. Here we are taking into account the rigidity or the stiffness of it and the mass of it, so we are getting a little bit closer to the realism we would want in a full model. But typically the dissipation is going to be, at least we consider it small, and it's difficult to calculate. So to get down to that bottom layer where we just have our equivalent mass or equivalent spring and we put the forcing on it, we're going to need to go through a couple of steps first. So let's first find, how do we find our K equivalent? So really we're using the idea of Lagrange here. We're still trying to find total potential energies, total kinetic energies when we do this. And KQ, same idea. But the only thing in this system that is going to have stiffness is going to be the deformable beam itself. So we can go and find its equivalent stiffness using the beam table. So bringing in the beam table, we have, this is our situation here. It's a cantilever beam, and the mass is going to be at the end of the cantilever part. So for the KEQ, we are interested in tracking this point, which is where that heavy mass, that point mass, is going to be located. So for this deflection here, I'm going to say, again, typically ignore this V max if it's on the table, even though actually we will get to that same exact point. The elastic curve is what we're going to more generally be using. So what we want is to establish what is the deflection at the point we're trying to track. So we want to be tracking V of L. Right? So again, if X is being measured from the left-hand side, we want V of L, and this is why we're going to use our elastic curve. So that's going to be this. I'm ignoring the negative sign here because I just care about the positive displacement right now. So I will have px squared, well, x is big L, over 6ei times 3L minus, again, L is equal to, or x is equal to L. So 2L minus L is going to be 2L. This is going to simplify then to PL cubed over 3EI. And the idea of a K equivalent is that it's going to be my displacement per the idea for the equivalent stiffness at this degree of freedom. It's going to be my force per the amount of deflection I have. So I'll call that delta, but here delta is going to be defined as V of L. The delta I'm using here and the delta I'm going to use when I'm establishing my equivalent or my effective mass, delta is V of L because X equals L, or this end point here is the degree of freedom I am trying to track. I ultimately want to find V of T. So that is important to put up here. What am I ultimately after? What is V of T? And V is, in this case, established at the end. Right, so rearranging this, and we've seen a cantilever before here. I want my P over delta, so this is going to be 3EI over L cubed. Right, so that's for these boundary conditions and for the point at the end of the cantilever, which I'm going to be calling that deflection delta. That's the degree of freedom I'm tracking. All right, so that is the only thing with stiffness, so that is our equivalent stiffness. So now we can worry about MEQ. All right, so we are going to, according to kind of the second layer of this model, this is going to be that rotor plus M effective, which is coming from the mass of the beam. So the mass of the rotor we were provided, and it is going to be 20 kilograms. And we still need the mass effective. That'll be our next step here. Now, if we look at the total mass of the tail, it's 240 kilograms. So that's over 10 times as much as the point mass that's resting on it. So this is a case where going into it, probably the mass of the tail is going to have a big influence to the equivalent mass of our system because it is 10 times as massive as the load it's carrying. So let's go about finding the effective mass. So we'll come back up to this. So we know that for kinetic energy, the only things that have kinetic energy here are going to be the point mass, and we will be accounting for the kinetic energy of the beam, the tail section. So M already is, big M is already located at the degree of freedom we're interested in. We're going from this top abstraction to the middle. How do we take all the mass in the beam and put it at one point, in this case the end, and have the two systems have the same kinetic energy? So this is where we use the idea that the kinetic energy, I'm just going to talk about the beam at this moment, is 1/2 the integral from 0 to L, M over L, times y of x dot squared dx. So that is the kinetic energy accounting for the distributed mass in the tail, and that's going to be equal to 1/2 M effective delta dot squared. Now here we can use the M over L because we are going to presume that the tail is homogeneous and the weight is going to be evenly distributed out. So this means that we can use a little bit of that shortcut, that the effective mass, because I can cancel out these 1/2s here, I can take m over L times the integral from 0 to L of y dot of x over delta dot quantity squared dx. And here the little m in this equation is going to be the total mass of the tail, which we were provided with. All right, so the inside of this integral is where we're going to need to do some work here. We need to establish what is our y dot of x. Well, first, we need to start with y of x. This is the deflection across the beam, everywhere in the beam. This, again, is coming from the elastic curve. So here I'm using y. In this table, it's using v. It's the same thing. It's just the deflection. So in general, this y of x is going to use the same thing that we used above, but it's just the general x version of it. So it's just going to be, again, ignoring the negative sign here, px squared over 6ei times 3l minus x. And the delta is the same thing as y of, in this case, big L. And actually that we've already calculated. That was the PL cubed over 3EI. Right, so the delta, the idea of the delta is the same thing here as it was for the spring constant. Delta is the deflection at the degree of freedom we're trying to track specifically. So this is actually asking for velocities, not positions. But what we can do is we can differentiate with respect to time. And we're going to get that y dot of x equals p dot. That's changing in time. X is not a function of time in this case. Here, x was defined as just my distance along the beam. So in this particular case, x is not a function of time, but y is. E and I we're saying are constant in time, so they're not affected. 3L minus x. And then here, same idea. If we differentiate both sides, the velocity at our chosen degree of freedom is going to be p dot L cubed 3EI, and that's it. Right, so again, we have this p dot that applied force can change in time, but it's not going to really matter for what we're calculating, because we want this fraction of y dot of x over delta dot. So if I take what I have so far, I have this p dot x squared times 3L minus x, and I have here 6EI, and I divide it by delta dot. Well, division is just multiplying by the reciprocal, so I'll have a 3EI, and I'll have a p dot L cubed. So for this ratio, for this division, the p dots are going to cancel. The stiffnesses are going to cancel. I have a 3 on top. I have a 2 on the bottom. So this is going to simplify down. And this is going to be x squared 3L minus x over 2L cubed. So this is the thing I am going to want to be doing the integral of to find my m effective. And so m effective, now that I know what that ratio is m over L. I'll do this generally first and then put in my values at the end, times this thing I just created, 3L minus x over 2L cubed, and that has to be squared dx. All right, so something like this I could do by hand, but I'm going to do it in Mathematica instead. So I'll sign MEF is going to be m, that's the mass of the entire tail section, divided by the length of the tail section. And I need to do the integral from 0 to L, and I have to put in this whole fraction now, and then I'm going to square it. So x squared 3L minus x over 2L cubed. This gets squared dx. All right, so we see here the effective mass. Actually, all the L's are going to cancel out when I do this. The effective mass is 33/140ths of the entire mass of the tail section. So we get 33/140 times m, and I will put tail here so we don't confuse it later. That is the effective mass. So we don't simply plop down the entirety of the mass of the beam on that one point, because we're not trying to make the masses equal, we're trying to make the kinetic energies equal. So for this system, we're going to put 33/140ths of the total mass there, and that will be the effective mass. We've now compensated for the mass of the tail in our picture. And then we are also going to need to know the forcing function that is acting. So we have this eccentric mass that's rotating. So our f of t, eccentric mass is rotating. We're going to use m. Here, this little m is the weight of that mass of the eccentric mass times its eccentricity times its angular velocity squared times, and here I'm going to use cosine omega t. Now my presumption is that at time 0 that the mass is going to be exerting full force downward. I could also use a sine or any sort of phase here. We're not told really the details, but this will be a good enough way to put it together for the purposes of this evaluation. Okay, so we've modeled the spring constant. We have modeled the equivalent mass. Now, in this case, we are told a little shortcut here. We are going to be having some damping from the tail section because we're told that it has a damping ratio of 0.15. So actually, we will need to use that knowledge in our model, but we can't do it quite yet. It's not going to come from a modeling step by finding it using a beam table or something. We're going to have to come back to it using that damping ratio. But we can start to put some things together. We have our KEQ, the MEQ now. We know this is 33/140 times the mass of the tail section. So that's all come together. And we have our F of t here. So we can go to our identify step. And we know there's going to be some CEQ as well. But we're not quite ready to solve for it yet. But we can now put together a general equation of motion. So in front of the x double dot term, we have our MEQ, which is m plus 33/140ths times the mass of the tail. And that will be times, I'll call it v, so v double dot, plus some c, or CEQ, I'll just leave it as c, times v dot. We're going to have to get the more details of that equivalent damping coefficient though. Plus, and then we have the stiffness, our equivalent K, which was 3EI over L cubed. Times our V equals ME omega squared cosine omega t. And now we can put in some more details since we have some of these values, the M total that were given to us. So we know that M was 20 kilograms. We know the mass of the tail was 240. So I can fill in and find that the total equivalent mass then is going to be 76.6 kilograms. So that's V double dot plus, I'll come back and fill in this in a moment, plus, right, so we are told that the flexural rigidity was 2.5 million Newton meters squared, so that's my EI, and our L was 4 meters. So our stiffness comes out to be 117,000 newtons per meter. So again, I will just operate in base units here. And now we have that eccentric mass that had a mass of 0.5 kilograms. And we were given that the eccentricity was 0.15 meters. And we have an angular velocity of 1500 RPM, or 157 radians per second. And we'll revisit this in a moment, but we can put this together too. That will be 1850 newtons times the cosine of 157 t. So looking at our equation of motion, and we can go and see our identify step of what we have going on here. So v is our one dependent variable, so it's 1 degree of freedom. It is going to be linear. It is going to be damped. We'll have to see, actually we know it's underdamped because we are told what the zeta value is going to be 0.15, so it is underdamped, we know that. And we have simple harmonic forcing on the right-hand side. Again, I'm just going to use a cosine for this for simplicity, but it could be a sine function, it could be a cosine with a phase delay as well. And it's going to turn out not to matter because we're just going to look at the steady state response of this anyway. So we know that at steady state, I'll call it VSS, the steady state value of those oscillations of that deflection is going to be x times cosine of omega t minus phi. So we need to calculate the x and the phi with our parameters. So let's start with our favorite, the natural frequency, which is going to be root k over m. Again, whenever I write this in the parameter step, I am talking about the equivalent values. So we do at this point have the full knowledge of our equivalent stiffness was 117,000 newtons per meter, and our mass 76.6 kilograms, which means we have a natural frequency of 39.1 radians per second. And it's a damped system, so we can look at our value of zeta is going to be c over 2m omega n. And actually we were told that this has a damping ratio of 0.15. The thing we don't know is c, the equivalent damping coefficient. So actually we can solve this for c and update our equation of motion because it's going to turn out that c has to be equal to 899 newton seconds per meter in order to have this value of zeta with this mass and this natural frequency. So I'm going to come back up here and update this to the 899 that we know it is. Now we have enough information to find the x and the phi for this system. So in general, x is going to be calculated using, we can use this equation here. I have f naught over square root of k minus m omega squared, and that quantity is going to be squared, plus cw squared. We just calculated our c, so now we can calculate this as well. All right, so we already know our f naught. That was the amplitude of our forcing function, 1850 newtons. And the k we calculated from the equivalent stiffness, 117,000. M we got from the equivalent mass, which was the mass of the rotor plus the effective mass from the tail section, so that's 76.6 kilograms. And C we got to be 899, and we know the driving frequency is 157 radians per second. So we get here that big X is 0.00104 meters. Now keep in mind this X value is dependent on the mass, the equivalent mass of our system M. This will come into play when we do a comparison in a moment. And phi is generally going to be the 4-quadrant arctangent of our CW divided by K minus M omega squared. And when we go through, and we'll verify this in MATLAB again, we get 3.06 radian. So when we put this all together, the steady state deflection V at the end of the cantilever, accounting for the mass of the beam itself, the distributed mass of that beam, is going to be 0.00104 times cosine 157 times t minus 3.06 radians. and this is going to be measured in meters. Going back to the top, this is what we were trying to find. Actually, more specifically than v of t, I will put here, we only want the steady state response, so VSS of t. And do note, for the weight of the tail rotor blades, I'm assuming that that 0.5 kilograms is included in the 20 kilograms. If it's not, it'll be a small adjustment. It would increase our effective mass a little bit by half of a kilogram and change the results only slightly. Going into the MATLAB, we can just verify some of the calculations that we had done by hand, just to make sure that everything is coming out correctly. So I'll run some of what I have so far here. All right, so I put in the rotor mass, the eccentric mass, the stiffness, some of these other parameters here. Just make sure our driving frequency, once converted, is 157 radians per second. I'm going to come here and calculate the effective mass. Now notice I'm doing it, this time I'm doing it in MATLAB, and I'm letting MATLAB do this integral step. So I'm using the integral command, and I'm putting in that exact expression here that I want to integrate. So this is the same thing I did before in Mathematica, where I got that nice fraction, that 33 over 140. But here I'm going to do it completely numerically. I already know it should be 33 over 140, but this will automatically calculate it for me. So the effective mass, I get that 56.6 or 56.5 kilograms. So when I add that to my point mass located also at that the end of the cantilever beam, I'm going to get the MEQ 76.57, 76.6, just like I had. Then I can go and look at the stiffness. Again, same calculations that I already did. I get that 117,000 to 3 digits of significance. Get the natural frequency, 39. Calculate that value of C, about 899. And my amplitude, 1850. Everything here is being shown in scientific notation. And the value of X that I calculated before. So 1.04 millimeters. And finally, the phase, calculating that again, positive 3.06 radians. Okay, so everything there matches great. Now, what I'm going to do for comparison is, again, I already know what my steady state should be. Here I'm calling it X just in the code for simplicity, but that's the V I was doing before. Is going to be X, the steady state is the amplitude times cosine omega t minus phi. All right, so this X is taking into account the mass of the tail. For contrast in this one, I am also going to see what the behavior looks like if I ignored the mass of the tail like we typically have been doing. So I'm calculating also this X2. So this is basically if I make M effective 0, then that means my M equivalent is just big M. So that's what I'm doing in 341, is I'm going to see what is X without taking into account the tail, and also what is the phase going to be, because here instead of MEQ, I'm just using big M. And then in 345, I am going to see what that trajectory looks like. And I'm going to plot these both on the same plot. So plotting it this way, I am going to do it for 3 periods of forcing. So that's what I'm defining here for my time. And when I plot it, notice I'm going to normalize this a little bit. I'm taking my time in seconds and I'm dividing it by the forcing period and multiplying it by 100. What I'm going to get out of this is basically percent of forcing period instead of absolute time. So it's just dividing my time by the forcing period, and I want it in percentage. And I'm going to plot my little x of t, which again, that is going to be taking into account the mass of the tail, and then x2 of t, where I am ignoring the mass of the tail, but plotting them just versus each other. So running all of this, I get my two plots here. So red is no tail weight is really what it's referring to, or not accounting for the mass of the tail, assuming it's negligible. Black is when we do account for the mass of the tail. So going into more detail, if we look at the peak, this is in millimeters the way I'm plotting it. When we did account for the mass of the tail, well, it should be just that capital X or very close to it. So 1.04 millimeters is the amplitude. It goes up and down by only a little bit more than a millimeter while it's running. Whereas had I neglected the mass of the tail, because the mass of the tail was so much, I'm seeing here that 4.6, and I can also just type it out here, 4.6 millimeters is going to be the amplitude when I don't account for the mass of the tail. So we see a pretty big difference here. It's over 4 times more amplitude is predicted when the tail is ignored than when we include it. So our analysis is thrown off by 400% if we don't account for the mass of the tail in this particular problem. And on top of that, maybe a little bit less important for what we're looking at here, but the phases are also a little bit different, but probably the amplitude would be more concerning. Because if we're making a decision, do we have to make a repair of this rotor because possibly the amplitude is getting too high for the tail, ignoring the mass of the tail section, then the amplitude we're predicting is much, much higher, and we might make a recommendation to take it out of service, do a repair, maybe prematurely, before this really would start to be a problem. So this is a case, and the clue really was at the beginning here, that pretty big massive tail, about 10 times the mass of the tail rotor section that's carrying, is a clue that we should be accounting for the mass of the beam or the mass of the distributed deformable body in general in this problem.